All right, so my name is Robert, and this is Armin, and today we'll be presenting to you our fourth-year design project, very aptly named, I believe, Antigen Detection using Fluorescence Quenching Competitive Immunoassay. So our objective was to quantitatively determine the concentration of a specific antigen in an arbitrary solution using our biosensing technique of choice. For the purpose of focus and for determining our customer requirements, we have taken upon the noble cause of diagnosing malaria. However, for the proof of concept, we shall be using the relatively inexpensive bovine serum albumin.
So now, what exactly is malaria? Malaria is simply a disease that is caused by parasites known as Plasmodium, of which 5 types can be transmitted to and by humans. The most common and deadly of these is known as Plasmodium falciparum, which was the cause of 80% of all malaria cases in 2012. At approximately half of the world population is at risk for contracting malaria, with 207 million cases of severe illness and almost 650,000 deaths in 2012. Some examples of antigens that we could use for the detection of malaria for diagnostic purposes are the histidine-rich protein 2 and the various existing heat shock proteins. Contributing to malarial resistance is the inaccurate identification of infection with current in-field testing methods. The current standard diagnostic methods include blood film microscopy and rapid diagnostic tests. The former is very sensitive, quantitative, and accurate. However, it requires a lab to perform highly trained professionals or personnel and is expensive and slow. The latter is today's best in-field method, being simple, rapid, and inexpensive. However, it only provides qualitative results and it is unreliable and inconsistent. So based on the above considerations, we have created the following list of requirements. Of utmost importance is the achievement of a limit of detection of less than 16.8 nanomolar. This value is simply based on the average plasma concentration of the histidine-rich protein 2 that we previously mentioned, which is an antigen associated with malaria. This is based on several patients' data. In addition to this, each test should take less than 20 minutes and should cost less than $5. These requirements are based on a desire to combine the simplicity and inexpensive and rapid nature of the rapid diagnostic test, as well as the sensitivity and quantitative nature of the microscopy testing. Of secondary importance would be to demonstrate a sensor selectivity. This would be done by interference testing. Normally, this would be a primary requirement. However, due to logistical issues with the testing and use of whole blood samples with any antigen in it, there were some difficulties in doing this. In addition to this, some lifetime analysis for the sustained efficacy of our chemical sensor would need to be performed over a duration of 2 weeks and a temperature range of 10 to 40 degrees Celsius. Finally, time permitting, we would attempt to develop a portable fluorometer that is compatible with our designed sensor for in-field use and compete a longer lifetime analysis over an extended period of 3 months.
Now, to fulfill all of these requirements we set out, we proposed the above mechanism. So on the far left, we have our gold nanoparticles with antibodies on their surface. It's important to note here that the image is mildly deceiving because within our synthesis procedure, no effort was placed in actually orienting the antibodies in any particular fashion. Now moving on, to this complex, we add fluorescently dye-labeled antigen. When the antigen binds to its corresponding antibody on the gold nanoparticle surface, this brings the dye and the gold nanoparticle closer together. Now, assuming that we have strong overlap between the emission of the dye and the absorption of the gold, we can have efficient quenching via Forster resonance energy transfer. Now, it is to this complex that we actually add our sample containing the free antigen, depicted as the little red triangle. And these little red antigens will then compete with the labeled antigens for the binding sites on the gold. So some of the labeled antigen will be liberated from the particle, and the extended distance between the dye and the gold nanoparticle will allow for fluorescence to occur.
So naturally, an important decision for us was to select the proper dye that is compatible and effective with our system. To ensure a strong quenching by FRET, we had to select a dye whose peak emission overlaps well with the peak absorption of our quencher, which in this case are our 20 nanometer diameter gold nanoparticles. The dye we have selected is called fluorescein isothiocyanate, or FITC, and as you can see on this graph, that we measured, the peak emission and its spectrum overlaps very well with our quencher, the gold nanoparticles.
So now, when it comes to actually experimentation, we completed quite a number of trials. We had ups and downs, and eventually we came up with a fairly reliable procedure. So we, over the course of the last few months, we manipulated many parameters, and we observed limits of detection ranging from anywhere between 0.4 to 5 nanomolar, typically. So examples of our trials can be seen here. On the left, we actually have basically the very first trial we ever completed. The data looks a bit rough around the edges, but at the time it was a good indication that we were headed in the correct direction because of the positive correlation between the fluorescence strength and the antigen concentration. Of course, sailing was not smooth, and sometimes later we also encountered issues like what we see on the right here. On the right, we have a fairly shallow slope, and this can be likely attributed to the photobleaching of the dye, which is something that FITC is specifically known for. Now, of course, like I said, we did complete a lot of process optimization. Examples of these include points listed here. In our initial synthesis procedure, we initially had 11 mercaptoendecanoic acid being functionalized on the surface of the gold nanoparticles before binding our antibodies. However, we deemed it unnecessary due to the amount of time it took to introduce it and the relative lack of a benefit compared to our other alternatives. When labeling our antigen with the dye, we also had to manipulate the molar ratio in which we added them, and of course we also had to play around with the dialysis procedure to make sure that all of our unbound dye was removed. Similarly, when adding antibodies to the gold nanoparticles, we would add excess antibody to ensure the binding, and we would have to centrifuge repeatedly to wash out the unbound antibodies. Going hand in hand with this is the optimization of the antibody to gold nanoparticle conjugation ratio, which I'll actually talk about right now. So we called this the gold flocculation test. To estimate the actual surface coverage of the antibodies on the gold nanoparticle, what we did was we added variable amounts of antibody to fixed concentrations of gold nanoparticles and allowed them to incubate for some time. After that, we added a large amount of salt to force the particles to aggregate if they could. And then we measured the absorption spectra. On the left here, you have the ideal data from literature. You can see that as the antibody concentration relative to that of the gold nanoparticles increases, the spectra of our gold nanoparticle antibody and salt concoction approaches that of the absorption of just pure unaggregated gold nanoparticles. So how we numerically actually defined how aggregated our particles were was by determining the difference between the absorbance at 520 and 580 nanometers, and our results can be seen here on the right. So we plotted the absorbance, the difference, against the antibody to gold nanoparticle molar ratio, and we can see that after a molar ratio of around 20, additional antibodies did not contribute significantly to the stability of the system. Therefore, for the actual concoction of our complexes, we use the 1:25 ratio of antibodies to gold nanoparticles.
So finally, after working out all of the several knots in our procedure, we came up with the following results. These are actually based on our most recent and promising results. We observed background noise levels of about 11 fluorescence units relative to everything else, a slope of 80 fluorescent units per nanomolar, which results in a limit of detection of 0.42 nanomolar following the regular 3 sigma convention. Additionally, if we assume the addition of 50 microliters of a test sample to 50 microliters of our testing solution, which yields a 0.2 nanomolar concentration of the complexes, the cost per test was estimated to be just over 6 cents. This is very reasonable, especially considering the fact that we obtained all the components for our chemical sensor in very small amounts, which is something you'd traditionally avoid for large-scale production. There are unfortunately still some limitations to our sensor's current state. The first and foremost of this are inconsistent laboratory results, which naturally we'd have to further improve our procedure to get more consistent data from our testing. Also, the sensor stability over a very long period of time is unknown, as only short periods of stability testing were performed. However, in similar literature data showing similar structures, they found that their detection capabilities were stable and effective over a time period of at least 1 month. And finally, although not a limitation of our sensor's detective capabilities itself, the production of antibodies themselves might present some kind of barrier in scaling up for more large-scale productions.
Now, there are a few areas of future work that we have identified. First and foremost, we need to further refine our procedure, especially with regards to our antibody washing procedure, in order to further reduce the background to increase the performance of our sensor. We also need to complete more testing to determine the working range, and we also need to start testing the nanoparticle concentrations associated with relevant diagnostic levels, and as well as complete interference testing with whole blood, as well as lifetime testing. Optionally, we should also investigate the use of alternative fluorophores with equal or greater quantum efficiencies, but with less propensity to photobleach.
Now, finally, venturing into our tertiary customer requirement, since we had some time remaining, some remaining funding, and felt like we needed another design project, we attempted to build an LED-based handheld fluorometer to couple with our chemical sensor. We couldn't simply buy a full-size device as they're very expensive and don't exactly fit in your pocket. The commercially available handheld models run from $1,000 to $3,000, which was significantly exceeding our remaining budget, so we had to build one ourselves. To do this, we employed the use of a very high-intensity light-emitting diode to replace typical sources such as xenon arc lamps and laser diodes. We used a photodiode-based detector coupled with a signal amplification and noise reduction done by circuitry, which would replace the commonly used photomultiplier tube-based detection and amplification methods. This would theoretically create a much more inexpensive and more compact handheld fluorometer. So for the selection of our fluorometer components, we chose an LED whose emission spectrum can be seen on the above graph to overlap fairly well with the peak absorbance of our dye-antigen complexes. A photodiode was also selected whose peak sensitivity would overlap well with the peak emission of this same complex. The responsivity of our photodiode can be seen on the below graph. We also chose to use excitation and emission filters to further reduce any background noise and selectively choose the wavelengths of range of the fluorescence for the photodiode to receive. We used a bandpass excitation filter which overlaps well with the absorption spectrum of our diantigen complex shown in blue on the top graph, and the emission filter was also a bandpass filter that fairly well overlaps the emission spectrum on the below graph shown in red. Finally, for the circuitry itself, we used what is known as a lock-in amplifier circuit. A simple block diagram of this can be shown here. How a lock-in amplifier works is basically it allows you to extract a signal based on a known carrier wave in an environment of significant noise levels. This is fairly ideal for our situation. It also makes it very insensitive to any ambient light conditions. How this actually works is the sample would be placed in between the LED and the diode shown by those little triangles with lines if you don't know what those symbols are. The LED excites this sample which fluoresces. This fluorescence is detected by the photodiode. The photodiode creates a photocurrent, which is converted to a voltage through the use of an ultra-low bias current DIFET. This is then passed through a high-pass filter to remove any DC component of the signal which is necessary for the proper functioning of the circuit. And finally, this is coupled with our known carrier signal, which is that of the LED, and processed by a synchronous demodulator. This is our final useful signal, which is then passed through a low-pass filter, effectively completing a narrow band pass around the frequency of importance to us. And this is finally amplified by a typical operational amplifier, and the output is red. After running some tests on our fluorometer in its current state, we found that it had detection in the fairly high micromolar range compared to similar designs which show nanomolar detection in literature, even up to limits of detection of 2 nanomolar. We weren't surprised by this as our circuitry was assembled on a breadboard and was unshielded, which contributes a significant amount of noise to the circuitry itself, as well as that the housing for the device itself was not ideally isolated from ambient light conditions. This being said, the signal we obtained out of our fluorometer is very clean, and it only cost us $120 to build. The bulk of this cost is actually the filters themselves, being $80 in total. Naturally, further testing and development would need to be done, primarily transferring the circuitry to a printed circuit board, properly shielding it from electromagnetic interference, and properly isolating the device itself from any ambient light conditions.
So now, in summary, just to reiterate what we've already presented, our biosensor was capable of determining a limit of detection of 0.42 nanomolar approximately, with a known linear range between 0.5 and 5 nanomolar. The cost per test, now this is based upon the prices that we ourselves paid for the materials, and assuming that we're adding a 50 microliter sample to 50 microliters of sensing solution. In this case, the cost per test would be a mere 6.3 cents. And although not noted earlier in our presentation, the actual readout time is on the order of minutes, provided that the sample is well mixed. Our portable fluorometer demonstrated the ability to detect dye on the micromolar concentration range. Although this is a far cry from the nanomolar range we were ideally hoping for, consideration has to be placed towards the cost. $120 is just a mere fraction of the $1,000 to $3,000 price tag associated with the commercial models available on the market right now. And of course, with all things considered, I would say our signal output was fairly clean. So now we're nearing the end of our presentation, but before that, I would like to make a few acknowledgements. First and foremost, we'd like to thank Professor Juwen Liu for allowing us to use his lab facility, as well as for his job as our project consultant. Additionally, we'd like to thank Professor Aziz and Jen Coggin for their vast time and effort contributions to the NE-FYDP in general. We'd also like to thank Professor Backhouse for his very generous contribution of tween 20. And we'd also like to thank, although not mentioned here, John Saad for allowing us to have access to instruments to allow us to test and demonstrate our fluorometer.
That's the conclusion of our presentation. Thank you for your attention. If you have any questions, please go ahead.
Questions from the audience?
Yes.
Okay, so the last presentation was just a lot of captors. So if you considered using captors instead of antigens to reduce your costs?
That is an option, and it would be really nice for a scale-up. However, in this case, we're detecting antigen, which are emitted by parasites, essentially, right? So we're using antibodies to detect the antigens. Antigens are fairly large structures, and aptamers are typically used for smaller molecule detection, I believe, right? So it wouldn't really be compatible. In this case, the antigens are also expressed they're pretty common in the blood of those individuals who are infected with the parasites. So it's something that we've known that is able to diagnose illnesses such as malaria and tuberculosis and so on and such forth.
Okay, I saw a switching behavior in your gold flocculation plot. I just realized that you had page numbers at the top right.
Okay.
What causes the switching?
Are they switching?
So basically, at about 2.5 micrograms per milliliter, everything is either in one state or the other at about the blue line. Something happens. What happens? Any thoughts on that?
Essentially, the surface coverage is such that the antibodies are not actually covering the surface sufficiently. So when we add the salt, this really forces the particles to come together, right? So if we were to add the salt to raw gold nanoparticles, they essentially clump up instantly.
Okay, right.
And
right,
yes.
Right. Got it. I was thinking that was your antigen, not your salt. Okay,
There we go.
Now I understand.
Okay.
And good works.
Any other questions?
Let's thank our speaker again.
Okay.